Ahoy mateys, and welcome back. Expedition 345 Hess Deep Rift has been out to sea for a few days now. It's taken 4 days to transit from port in Costa Rica to the first site, and we can't wait to start drilling. You may be wondering what's so important about this place, so I'll tell you. The Hess Deep Rift location is a very special one because it gives us a glimpse through the tectonic window. The tip of the Nazca Coco Rift is propagating like wedge into the Pacific Plate. The material that is located below the surface is being pulled up in this rift zone. There are only a few locations like this one on the ocean floor, so it's very rare. Usually, in other parts of the sea floor in the Pacific, you'd have to first drill through lavas and basilic-sheeted dike layer to finally reach the gabbros. In the past, our drilling machinery has access to uppermost gabbros. But the unique thing about the Hess Deep Rift is that we have a direct way to access the gabbro layer because of the way the plates are interacting. This interaction allows us to study, explore, and collect new data. Honestly, we have no clue about how the crust in this location is formed. Well, actually we do have some. What we do know about the ocean crust is it's made up of a layer of sediment, lavas, dikes, and gabbros. We know this because we have sections of ancient oceanic crust exposed on land that are considered to have formed similarly to modern oceanic crust. Scientists back in the 70s used tools to measure the speeds of which waves pass through the crust. They were measuring seismic velocity. From their experiments and the observation from the oceanic crust, they were able to tell that different densities or layers were present, one of which included gabbro rock. Gabbro has a relatively slow crystallization process, and it was decided that a huge magma chamber must be present. The problem is, no one can find this massive reservoir of magma. Over the years, scientists have detected a small magma chamber on top of the magmatic mush portion. This mush is made up of crystals and melt, which is basically molten rock. The small magma chamber, or melt lens, helps to explain the low seismic velocities, but now the scientists were tasked with having to explain how such a small melt lens could produce such a large amount of gabbros. One of the explanations is referred to as the gabbro glacier model. This model includes a mush zone. In this zone, melt is transported up towards the melt lens that sits on top of the gabbro section, and all the crystallization happens within this lens. Crystals formed during cooling when cold seawater goes through the rocks on top of the melt lens. There it is heated up and rises again to the sea floor, taking away the heat from the magma chamber. The crystals are transported down and out through the mush zone, but some people see a reason to believe that crystals are also forming at lower levels. So another model, called the sheeted sill model, suggests that there are a series of melt lenses throughout the mush zone. Melt is transported upwards, but then cools in various areas to form crystals and gabbros. But with this model, you would need a way for the cool water to reach the lower parts of the crust, close to the ridge's axis, to efficiently cool the newly formed gabbros. And we are out here to test if that's what's happening. By drilling at the Hess Deep Rift, we are hoping to figure out where crystals are formed. The gabbro glacier model suggests that all of the crystallization happens at the top, and the sheeted sill suggests that it happens all over at different depths of the ocean crusts. But as of now, we have no continuous samples to test these models. We won't know until we start drilling. Perhaps the observations we find during this expedition will help us test and maybe even revise the models. We'll have to wait and see what we find. Yar!